So in this video, we're going to give a brief look at a hint for problem 10 from the chapter 5 homework. And this is a hard problem, not necessarily because the underlying statics is hard, but you may have been intimidated feeling like there were too many unknowns to set up the problem. But this is a problem type that occurs a lot throughout the standard statics texts, both Hebler, which is the one we're not using this semester, along with Beer and Johnston. I forget which one's which. We're using one of the two this semester, but miraculously, what you find is wherever you take this course, you use one of those two books. They're used everywhere. And the problems, a set of the problems tend to be like this, where they're carefully designed such that it looks like you can't solve them originally, but if you just follow through your process and enforce your equilibrium conditions, they eventually lend themselves to some sort of numerical solution. And actually, when someone came in and asked me about this problem today, I was thinking about a problem from the Hebler dynamics text. So for those of you that are going to go on and take dynamics, where there's actually a system of equations where one of the unknowns, it's similar to this, and you have to solve a set of equations numerically in order to solve for the solution. It turns out that this is better designed. You don't have to solve numerically. In fact, all that you have to do is factor a quadratic equation. So how do we go about doing it? So we're trying to find the distance. So we have a distributed load, and it's characterized by this parameter A. And we want to find A such that the two vertical reactions of these supports are equal. So A, if you look at the reaction at support A, it can provide a horizontal reaction, but as is the case for most beams, when you have a purely distributed load, the horizontal component won't be zero. So you basically want to figure out how much can that A spread along, or how much does that A parameter need to spread along in order for the two vertical reactions to be equal to one another. So the first thing you want to do whenever you're working with distributed loads is remember that it's going to be overly complicated if you try to carry the distributed loads around. So replace them with concentrated loads. And I know that since the width of this first portion of the composite area is defined by A, and by definition, the width of the second will be as well, it's still better to work them in terms of a variable A and deal with a single concentrated force versus carrying those distributions around. So first thing first, I would take the leftmost triangle, the first portion of the composite, and replace it by a concentrated load. You need the area under the curve, which is just going to be 1/2 the base, which is that unknown A, times the height, which is 1800 newtons per meter. Half of 1800 is 900. So this area, or the magnitude of the concentrated load corresponding to this portion of the distribution, is 900A. It's whatever A is, the larger A, the larger that load will be. And in terms of this composite portion of the distribution, we're going to note that the actual width of it is going to be the total length of the beam, which is 4 minus A. So this is 4 minus A wide. It has a height of 600 Newton per meter. When you do 1/2 base times height, that's going to give you 300 times quantity, 4 minus A. I'm going to leave it not multiplied out for now, but we'll see eventually we have to. So now we can draw a simplified free body diagram. Yeah, it has some parameters in it. For example, the magnitude of this force is 900 times A. It's located at A over 3 because remember, for a triangle, it's 1/3 of the way along the base from the peak height. So this is A wide, so it's going to be A over 3 from the leftmost side. For this triangle, it's going to be the base, which is 4 minus A divided by 3 from the left-hand side. So rather than using a common coordinate system here, I'm just kind of, in the sense of my free body diagram, just labeling these in for now, because I wasn't asked to enter those centroids in a system that's going to be graded like the last example we did, where you would have to have your values referenced from a coordinate system. As long as you can tell for your free body diagram what the meaning of your parameters are, you're good to go. So how could we actually, how do we need to go about doing this? Well, I didn't even have to draw AX, because if I sum all forces in the X direction, I'll find that AX has to be 0. So what equilibrium conditions should we enforce? Well, let's just start enforcing some. And let's start with summing all forces in the vertical direction, which basically says however much those two concentrated loads are pushing it down, that has to be amount that the two vertical reactions are pushing it up. So AY plus BY equals the sum of the magnitude of the two concentrated loads. Now you can actually distribute and do some simplifying math. 300 times 4 is 1200. 300 times minus A is minus 300A. Plus 900A gives me 600A. So it looks like I just got a bunch of mumbo jumbo alphabet soup going on here. However, remember that we're solving for equilibrium such that these two reactions are going to be equal. So rather than carry around two variables, AY and BY, I'm just going to call each of those R. So really, I want those two to be equal. So 2 times R has to be equal to 600A plus 1200. Isolate R by dividing by 2, and you get that equal unknown reaction as a function of A is 300 times A plus 600. So it's not typical like we usually do these problems, but you're still getting an equation in two variables. You don't know R and you don't know A. And whenever you have an equation in two variables, you want to try to eliminate one of the two. Now, it just so happens if you choose to sum all moments about point B now, and what that is going to be basically say, if you're summing all moments about point B using a counterclockwise positive convention, AY is going to induce clockwise rotation, and that is offsetting the tendency of those two distributed loads to induce let's try that again. If you think about it, summing all the moments about point B, AY is going to introduce clockwise rotation. The two concentrated loads are going to introduce counterclockwise rotation. So they're basically balancing each other out. This is pushing it up. These are pushing it down the other way. I like how I assume you'll be able to follow my hand motions, but hopefully sometimes when I do them slowly, you're able to get something out of it. So in terms of summing all the moments about point B, notice that the perpendicular distance for A is just going to be the length of the beam, which we know to be 4. The actual force is that unknown R. So if you're like, hey, why isn't AY? Where did R come from? Remember, that's the value we're using for the common vertical reaction. It's going to be a minus because if you pin at A and then pin at B and then push up at A, you're going to get clockwise rotation, and counterclockwise positive is our convention. These two concentrated forces are going to introduce counterclockwise rotation, so they both get positives. The 900A, what is its perpendicular distance? How far is it away from B? Well, it's the entire beam length, which is 4, minus this A over 3, which is how far away the centroid is from the A location. So I have 4 minus A over 3, that's my perpendicular distance, times 900A. For this concentrated force, its magnitude is 300 times quantity, 4 minus A, and the perpendicular distance is just the direct centroid that we computed above, 4 minus A divided by 3. If we do some arithmetic here, the factor of 3 cancels with 300, gives us 100. Go through and do your distribution. 900A times 4 is 3600A. 900A times minus A over 3 is going to be minus 300A squared. 3 cancels into 900 300 times, and you got the A times A, which gives you your A squared. I know you all know how to do algebra, so I won't read this out for you, but basically take this all the way and get it into quadratic form with the R isolated. Now, you might ask yourself, why would I ever want to isolate the R? Well, ultimately, I want to get rid of the R. I'm interested in solving for A. And in equation 1, I have R as a function of A. If I can manipulate this and get R as a function of A, I can set those two things equal to one another. And that's exactly what we're going to do here. If we set these two things equal to one another, what you notice is that 300A plus 600 must be equal to minus 50A squared plus 700A plus 400. It's an ugly one, but that's a quadratic equation. So you want to get it in standard form. Take all the terms to one side. When the minus 50A squared comes to the left, it becomes plus 50A squared. Combine your A's. 300 minus 700 is minus 400. Combine your constant terms. 600 minus 400 is 200. Factor out the factor of 50, which is going to leave you with 8A squared, minus 8A plus 4. When you take 200 and divide by 50, you get 4. Minus 400 divided by 50, you get minus 8, and so on. You know how to solve a quadratic. You will get two solutions if you solve that. But given the length of the beam, only one of the two is going to be feasible. So that's how you set that up. Even though the math is a little bit confusing with respect to the approach, the underlying statics is pretty simple because when you're replacing those distributed forces by concentrated forces, you're just dealing with triangles, and it's a pretty easy problem.